Hello everyone! In this video we're going to be talking about some of the common errors that programmers make while they're programming in C. We separate these errors into three different categories called compile time errors, runtime errors, and logical errors. And each of these are based on when the error becomes apparent to the programmer. So compile time errors show up while a program is being compiled. And syntax errors are a type of compiler time error. Runtime errors become apparent while the program is running, and most of the time it results in a crash. With a logical error, the program will compile and run, but it produces incorrect output. Something in the program logic is incorrect. So let's look at some common types. Here's a listing of some common errors, and I've pulled up in our IDE our blank test program so that we can try some of them out and just to see what they would look like. So let's look at this first one. This one says a common error is an unterminated string. That's what happens if you have a print statement that has an opening quotation but no terminating quotation. And that produces a compile time error, meaning that when we compile the program, we should see that error right away. So there's an opening quotation, but no terminating condition. So if we compile, we should see a compile time error. And the compiler puts this little red box next to the issue, which says, hey, I found an issue on this line, on line 12. And in the build message, it tries to tell you what went wrong. So here it tells us we're missing the terminating quotation character. So if we go back in and we put in the terminating quotation and try to compile again, that will fix all of our problems. And now we can build and run without encountering any problems. Okay, let's look at the next one. This one is a missing semicolon. This is a very common error. And that just happens if you forget to include the semicolon at the end of a statement. Now, all statements in C, for the most part, end with this semicolon. Now, if we forget, again, the compiler is going to put up a box where it noticed the problem. So it made it all the way to line 14 before it realized that we were missing a semicolon. And here in our build messages, it says, I expected a semicolon before the return statement. So we need to go see what's before the return statement to find out where we missed our semicolon. So once we put it back in, that will fix our compiler time error and we can compile with no problem. A common logical error is using incorrect percent codes. So remember, all of our data types have their own individual percent codes, and if we use the wrong one, we sometimes see some weird output. This is a logical error, so the program won't crash, it will compile, but it's going to produce an output that we don't expect. So let's look at an example. Let's create a float value with some real number and see what happens if we print it out using an incorrect percent code. So x is a float, it's equal to 5.5. If we print it out using an integer percent code, you can see that it printed out 0 instead of 5.5 or even just 5. It just prints out something that is wrong. But if we go back and use the correct percent code, then our output looks just fine. Okay. A common runtime error is missing the ampersand in our scan format functions. So print format functions do not have ampersands, but scanfs do. So say we had this value and we wanted to ask the user for it instead. We said it's a float, so we can hold a real number. We'll ask them to enter a real number for us. We'll scan it in. It's a float, so we're going to scan it in using %f. We should have an ampersand, but to demonstrate the error, we're going to leave it out for right now. And we're just going to print that output back out so that we can see it. So this is a runtime error, meaning the code will compile. It has started running. It's prompted us for information. It says enter a real number. Now if we try to enter a real number, because the ampersand is missing, we're going to see something like this. Our program has crashed. It's stopped working. Of course, if you have Windows, it's going to try and solve that problem for you, but it's a problem that we can recognize. You can also see if you're running a PC that it returns an error message. We're used to seeing process returned 0, but this time there was an error. So this value is something else. It's not 0. That indicates there was a problem with our program. So again, that's fixed by putting the ampersand in the scan format function. With the ampersand back in the scan format function, if we run our program, it should run without errors. Okay, let's look at some other ones. These are some common errors. Here's another set of common errors. The first two on this page are related to this idea called sequential execution. And that's what C programming does. Everything inside a program happens in the order that we specify, including our variable declarations and our initializations. So this first one demonstrates what happens if we fail to initialize a variable. So we're going to swap these out so it looks like what's on the slide. We have a variable x, a variable y that should take on the value of x plus 6. And we're just going to print out what y is equal to, a simple little print statement. So let's think about what's happening in these two lines. We've declared a variable x, but we haven't done anything else. We haven't given it a value, which means the computer is just going to try and find a value for it somewhere. It's commonly called a garbage value. It's not something that we want to be there. It's just whatever happens to be sitting in your computer. It's usually detritus. So if we don't initialize, the computer is just going to come up with a value from somewhere in the system. And what we're going to get when we add 6 to it is whatever that random value that it found is plus 6. So if we compile and run it, we're going to see here in this particular example, if you do this on your system, it might look different. My garbage value was apparently 48 because it added 6 to it, and we're printing out now that y is equal to 54. So again, this is something that we can easily fix by giving an initial value to our variable. If we want it to have an initial value of 10, then we can give it that. And then when we print out y is equal to 10 plus 6, or 16. It's always a good idea to initialize your variables. And if you don't know what you want them to be eventually, then initializing them to 0 is a safe bet. Now the second error, like I said, is related. This is out of order expressions. This is because C will do things in the order that we tell it to. So in this particular example, it will declare x, and then it will try to add 6 to x and store that answer in y. So remember, we're going to get x is some random value from the system. Y is now random value plus 6. And then it sets x equal to 4. Now this doesn't go back and retroactively fix y equal to x plus 6. It's just x is now 4 from here on out. So here's it copied over into the IDE. We've declared x, we set y equal to x plus 6, and then we set x equal to 4. So if we run it, we're not going to see y equal to 10 like what we're looking for. Instead, x has a random value to start with. Y is assigned the value of that random value plus 6, and then x becomes 4 after that. So one of the things you have to pay attention to while you're programming is the order of your statements. If you want y to be equal to 4 plus 6, then you have to set x equal to 4 before you do the addition. And if we do those in the order that we want them to happen in, then we're going to see a result that matches our expectations. Y is equal to 4 plus 6, y is equal to 10. We've talked a little bit about integer division already, but it's a really common logical error because it's hard to remember that C has two different types of division, integer division and real division. But if we intended real division but we accidentally do integer division, then we're going to see a logical error, like in our trapezoid example, where it printed out the answer was 0 instead of being a part of a real number. A final common error has to do with our preprocessor directives, in particular our define statements. Defines do not have semicolons in them. If you add a semicolon to your define statement, you'll see some weird things. So as an example, this is the incorrect version. Say y is equal to pi. We'll try to print out y is equal to pi, but there's a semicolon in our define statement. So this is a compile time error. If we try to compile the program, it tells us there's a problem somewhere in this statement, and it's telling us that it expected a parentheses before a semicolon, which is hard to pick out because we have that, but that's because what we're not seeing is the way this pound define works. And what it does is it replaces every instance of this in our program with this. So what it's actually seeing here, what the compiler is seeing, is 3.14 semicolon. So it thinks the statement is ending early with this extra semicolon. So if we take that back out, if we fix our define statement to just be pound define space name space value, no semicolon, then it should work just the way we expect it to, except we're currently printing y as an integer. So since pi is a real number, we need to swap that as well. So now y is equal to pi. Pi is a real number. And if we build this program, it should work the way we expect it to. We should see y is equal to 3.14. Okay, those are some common errors to keep in mind as you're programming. The only thing we want to add to that is a couple of extra pieces of information. The first is this idea of literals. Literal values are not stored in variables. We use those in most of our expressions. So you've seen several of these already. There are integer literals, which we used in our example of y equal to x plus 6. 6 is not stored anywhere, but it is an integer value, so it's an integer literal. We can also have real number literals like floats and doubles. Those are real numbers, for example, x plus 6.4. But we can also have character literals. Those happen in single quotation marks. So you can see here this literal character y in single quotations, that is a character, y, and we can have string literals, which happen in double quotations. So everything in between these two double quotes is a string literal. So single quotes for a single character, double quotes for a string. Okay. To finish off chapter 6, we want to talk a little bit about style and documentation. For the most part, programming style is what you uniquely bring to your programs. Style is, for the most part, up to you. But there are some common ways that we use to make our programs easier to read. One of those ways is comments. So comments are very important, and this just says when you should use comments. You should always have a header comment. The header comment tells anybody who opens your program right away who wrote it, what it was written for. We should also comment each major section of code, and we've split sections up so far as variables, input, calculations, and output, and that's a good idea. But as our sections get bigger, we'll need more comments to describe what each part is doing. So a good general rule of thumb is at least one comment per 10 lines of code. You'll also want to add a comment if you have to walk away from your program. If you leave part of it unfinished, you can leave a note for yourself that lets you know what you were working on and what you need to pick back up later. You'll also want to add comments if you do something a little bit out of the ordinary. If you make any unusual solutions or particularly complicated sections of code, you'll want to add a comment just to describe what's going on there. Comments provide documentation both for you and for other programmers. Of course, in this class, most everything you write is for you, me, and the TAs to read. But if you go on to have a job programming, you'll need to write comments for your team members and other people that write code with you. You'll also want to make sure that beyond comments, your code is easy to read. So here are some style conventions that help with readability. You want to use white space to separate sections of your code. And white space is a very literal term. The space between these two lines is white in this particular IDE. So this is what we mean by white space. There is one line of white space between this integer declaration and this print format function. So adding white space just helps separate sections of your code. You also want to indent code between corresponding braces. This helps indicate that something is inside something else. So in here, all of these statements in our main function are inside main because they've all been indented once. So it's very easy to see that this variable declaration is a part of main because it's been indented from where main starts. We also want to give our variables meaningful names, which helps save time if we have to read our code. So if we write a function that calculates an average, we'll probably call that variable average. So anytime we're looking at it, we'll go, oh, that very clearly represents the average. And we did this in our inches program. Every time we saw inches in foot, we knew that it represented the number of inches in a foot. We'll also want to use constants when appropriate and use some sort of stylistic convention that separates constants from variables. Now I use full capitalization for my constants and full lowercase for my variables, which clearly sets the two of them apart. But if you want to experiment with camel case and other options, that's totally up to you. So as a final note, this is about when white space matters. For the most part, your compiler will ignore white space. That's purely for you and other human readers of your code. But it does matter in some very specific situations. The first is any define statements. The white space is important here to separate the name of your constant from the define and the value of your constant from the name. And since there's no semicolon, this is all of the syntax. Pound define, space, name, space, value, and that's it. White space also matters in variable names in that it can't be there. So you cannot put spaces in variable names. It doesn't work. That's why we used underscores in inches and foot. Can't have spaces in your variable names. Alright guys, that's the end of chapter 6. In our next chapter, we'll start exploring conditional expressions and if statements, and I will see you then.